to deliver a talk in this FDP on such a short notice. Welcome, ma'am.
Thank you, madam, for the invitation, and good evening to all of you. So we can start our presentation. So in today's session, we will be discussing with what is a key management and what is its role in the IoT security, and what are the different types of the key management and the different solutions that the existing that can be used to enhance the IoT security. So I will be sharing the screen and the PPTs. Hope the screen is shared and visible to all.
Yes, ma'am, it's visible.
A very warm good evening to all of you. So in today's session, we will be discussing with the role of the key management in IoT security. So this is the outline of our session in which we will be discussing with the importance of the IoT-based wireless sensor network in smart cities. And then after that, we'll be discussing with the need of the key management and why the key management is important, why it needs to be studied, then the different requirements whenever we are designing any key management for any of the IoT based structure, then what are the different requirements of a key management scheme, then different threats that are there in the IoT. After that, we'll be discussing with the different classes of the key management schemes. They will start with the group key management. Then we will be discussing with the pair-wise key management, where there will be the keys that are set up between the two pair of devices. After that, we will be discussing with the different existing solutions for the key management. In it, we'll be focusing on the hybrid key management. Then we'll discussing another property of the key management, that is the key revocation. Then we will go on with attack model based key management, where we'll be discussing with that instead of proposing any key management, we have to first study the adversary behavior of that particular infrastructure, of that system. And if we are able to incorporate that adversary behavior, then we will be able to develop a very efficient and efficient defensive mechanism for that particular attack. So initially we will be studying the behavior, and after studying the behavior, we will be proposing a key management for that. After that, if we are not able to have a symmetric key between the two nodes, then we can go for path key establishment. So some part of the path key establishment will also be discussed. Next, we will be discussing with how the different techniques they can be they can be combined together to increase the performance of the resulting key management. After that, we'll be winding our session with the hashed key management scheme. So the first thing is that integration of wireless sensor network in IoT applications in smart cities. So why we are discussing with the IoT, why we are discussing with the security, why we are discussing with the wireless sensor network. So firstly, we will start with the definition of an IoT. So IoT is basically the connectivity of the various physical devices and the objects that are connected over the internet network, that are connected over the internet. So obviously it means that the large volume of data is generated by the edge devices, and that the data has to be secured, that data has to be preserved, and the privacy of the users and all the challenges that will be incorporated when we are talking of an IoT. So the major goal of an IoT is that we want to have a high degree of intelligence, where we want that there should be least human intervention. So basically we want the automation and intelligence in all the sectors of the life, making it very comfortable in context with the smart cities. It covers a large domain and every aspect of the society, that can be from industry, healthcare, intelligence, transport, then we have an agriculture, home environments. So we have large number of we have seen a large number of applications in context with the smart city when we are talking of an IoT. So the applications, it might be some industry applications. The application, they may range from an healthcare, transport, agriculture, home environment. We have large number of applications. So a smart city, it will cover all the domains that we are discussing of the society that will use the information and the different communication technologies. Now, here there is a challenge. When we are talking of the different communication technology, the problem is that every domain is using its own set of protocols, own set of security features, and its own, and it is generating a large volume of data. Now how that particular applications, they will connect with each other, and how we can means we can analyze the information, and how that information can be made confidential. So that is the main important aspect of of that IoT applications, that how we can secure the IoT, right? So in context with that, wireless sensor network, we have seen in the different application that wireless sensor network has emerged as the backbone of IoT, without which the concept of the smart city, we cannot realize that concept, because we have a large number of sensors, and we have the actuators that are being the edge devices that are interacting with the physical world, and they will obviously impose some changes. They are imposing different kind of challenges. So if we want to summarize, a smart city is a consist of a large number of heterogeneous devices, and each will have its own capability, each will have its own properties, and that can range from a very smart device, and can be a very simple object also. So what is the resulting of what is the result of the integration and collection of the different devices? That a large amount of data is gathered due to a large number of sensors that are connected to the objects. So IoT network, if you are talking in context with the smart city, it should be scalable. Scalable means, because here a large number of devices, they are they can be they can be added at any time. So whatever the protocol, whatever the defensive mechanism which we are talking of, or we are trying to develop or design, it should be scalable. It should be able to incorporate all the devices that are valid and that are authentic and that can be added into that particular network. So whenever we are talking of some network design, there is a requirement that we can add the new devices, and even we that mechanism should provide a provide a provision that we can delete the old devices anytime, anywhere. So due to the wide application areas and the difference of the technologies among the devices, incorporating the wireless sensor network becomes a very challenging issue in context with the smart cities. So if we want to summarize the different challenges of IoT, then it can be the interoperability, because different domains, different sectors that are connected in a smart city, they have their own set of protocols. So obviously how the different sectors, they will be communicating with one another, exchanging the data, that is a very major challenge. Second is the scalability. So whenever we are designing any mechanism, it should be scalable. It should be able to add any number of devices anytime, and it can be at any place. Next is how we can manage the large volume of data. As we have seen that we have the sensors and actuators that act as an edge device, that act as a terminal. So these devices, they are generating a large volume of data. Now, which device will have the responsibility of handling that large volume of data? How the data will be handled? So, and how the security and privacy is maintained? How that integrity and how is maintained? That will also be a very important concept. Second concept is that which entity is handling that volume of data, which entity is providing the security. So that is also a major challenge. It can be an edge device. If you are talking of the small terminals, they can also process some volume of data, or it can be some middleware layer that will be generally dealing with a large volume of data. So where that particular responsibility is given to which entity in that particular network, that is also a very important one. Next is the dynamic adaptation. Whatever the data that is generated, it has to, the mechanism has to be reliable, and it should have a least latency. That is also a major challenge. What happened is that generally we are proposing a large number of defensive mechanisms for IoT security, but what happened is that they generally suffer from a large latency, because the whatever we are designing, we have not incorporating the real time information. Whenever we are designing something, we have to check it in the real time application, so that we can say that what will be the latency. So latency is also a major role, and we have seen that mechanisms, they generally suffer from low processing and computation overhead and a large latency. Next will be, this is a generalized, we can say, this is a generalized open architecture of a smart city, where we have seen that there are different sectors that are connected with the gateway. Here, what we have seen that there is a large processing of data that is done at the terminals and terminal devices, and that will be supporting the critical applications like healthcare, then smart homes, then we have industry applications also. So here some data, it cannot be handled at the edge level. What we have seen from that particular diagram, from that particular figure, that some of the data, it is handled at the edge devices, and some of the data, it cannot be handled at the edge devices, so it will be handled at the middle layer, what we call it as a fog computing. So in that generalized model, what we have seen is that different sectors, it should, whatever the mechanism that we want to develop for that particular application, for that smart city, it should have, first thing is it should be scalable. The devices, they can add into the network, they can be deleted from the network. Second thing is that it should be it should support the heterogeneity of the different network protocols. Third one is that it should have an effective data storage is also required, because what we have seen that a large volume of data, it is created. So when a large volume of data is created, then effective storage is required. And
Priyanka ma'am,
yes, ma'am.
just 1 second. Manisha, Antil and Pooja, please mute yourself. Manisha and Pooja, are you there? Kuldeep, are you there in the meeting? Kuldeep? Kavita madam? I think they are not there. They are disturbing all the participants. Manisha, Antil and Pooja. Ma'am, you can continue. Let me try another method.
Okay, what we have seen that we have the different applications. The applications in the smart cities, they may have transport. In the transport sector, we have the smart parking is one of the application, IoT, uh, IoT application. Then we have the traffic monitoring. We can also say that smart light monitoring or this on the streets is also an IoT application. And what we have seen that intelligent road detecting traffic, that smart logistic. So we have seen a large number of IoT based applications in terms of the transport sector. If you are talking of agriculture, then we see that smart control of climatic conditions, then water level controls. So all in all, what we are talking is that IoT has emerged a major role when we are talking of a smart city. Then because it leads to not only the sensing of the data, it leads to further analysis of the data, and then the network communication. So that IoT, it deals with the three things. One is the sensing of the data, then analysis of the data, and after that the network communication. That all these things, they are incorporated by the any of the IoT applications. So if we are talking of major security issues in IoT, that may lead to the first issue is the data confidentiality. Whatever the data that is generated by the devices, it has to be confidential. Different approaches, it can be used to make the data confidential. But the main requirement, whatever we are designing, it should be able to, it should have a least overhead. If you are talking of the terminal devices, it should have the least overhead. Next one is the trust management. So different algorithms can be there where if you are talking of some entities that are means gathering the data, that are analyzing the data, obviously some mechanism should be developed for the trust management. Second is that how we can assess the network, how the different users, they can assess the network based on some wireless sensor network based IoT, that how we can make that access secure. Then we are talking of the secure data communication and access control and user control. So for that, we are talking, we are straight away coming to our main focus. Our main issue that we are talking is, or we will be discussing in that session, that is the key management mechanism for IoT. In the key management mechanism for IoT, we will be primarily focusing on the pre-distribution part, that how the keys can be shared among the different entities. And here we will be focusing on the symmetric key encryption. So if we can generally classify the key management mechanism for any of the IoT application, so we have found that majorly we can classify them into four methods. The first method may be a client class. It will transfer the identical shared key as a class of servers. And second will be where we will assume that here the server has the shared key. So here the problem is that each client will be keeping a single key for each server. And third one is that it will permit the client to maintain its shared key. So here in all the methods, what we have seen, that where the key is generated, how the key is distributed, and how the key is managed. So that is different. And that will add the complexity of the underlying mechanism. So key management, obviously, it will play a major role, because the key management, we can talk of it, it will be have different phases. It will start with the key distribution, where we will be, firstly we will be generating the key. If you are talking of that two parties, they will be sharing the same key. And after that generation, then how the key is distributed. Because if the key is not distributed in a secure manner, then whatever the algorithm, whatever the encryption algorithm we are using, it will be of no effect. Because if the adversary or the attacker got that particular key, obviously whatever the algorithm we are using, it can crack that algorithm, it can eavesdrop that particular data, and it can get the data. So here how the key is distributed, it is a very important concept. That's why there is a need that we have to study the key management. We have a large number of security algorithms in the literature, but how the particular key, that is a very important in some in the symmetric key encryption algorithms, that how that key will be managed, that will be distributed. It is also a very important factor in deciding the security of the overall mechanism. Now the last process, if we are talking, is that it will permit the client and server to communicate a standard pre-shared key. So again, we have recognized that the application of the shared key strategies and share key utilizing effects, that if we are talking that the two parties, they will be sharing some keys, different factors have to be incorporated. They may range from the allocation. Allocation means how the key will be given or assigned to the different devices. Then what will be the overhead, because uh, even whenever we want to transfer any data, either we will be generating the key at every session, or we will be generating the key once, and after some time we will be going for the renewal of that particular key. So obviously that will come into the overhead in terms of communication, overhead in terms of the processing at the edge devices, communication over a network channel. Then will be the stability will be like the life cycle. We can say that what will be the life cycle of that particular key, and when and how we will be changing the key, what will be the different circumstances that may lead to the changing of the key. Here we are talking of the wireless sensor network based IoT. Then obviously whatever the key management we are designing for the wireless sensor network based IoT, it should be scalable, and authentication is also done and should be extendable also. So whenever we are designing any key management for an IoT, it should have these particular effects has to be studied, like namely allocation, overhead, stability, scalability, authentication, and extendability. So before discussing with the key management, we will be discussing within some of the security issues that the different IoT applications they may face. So what we have seen is that in the development of any IoT application, security and the testing framework, they play a very important role. So first thing is the IoT security data encryption. So whenever we are talking of IoT security, the first thing is data encryption. Internet of Thing applications, they will collect a large amount of data. That data retrieval and processing is a very integral part of the whole IoT environment. So that data has to be protected. And how it can be protected? It can be protected using different encryption algorithms. Next is, in the context with the IoT security, we are talking of data authentication. So if we are talking of that, even if we have encrypted the data, then after the successful encryption of the data, the chances of device itself can being hacked still exist. So if there should be some way that the mechanism, it can establish the authenticity of the data that is being communicated to and from the IoT device, so that the security, it may not be compromised. So here the data authentication is also an important concept, and we have different mechanisms that will provide the data authentication. In context with IoT security, the next thing is the side channel attacks. Even if we have encryption, we have encrypted the data, we have provided the authentication also at both on both the parties that are connecting through an IoT platform, still we have some side channel attacks. So these attacks, they focus less on the information, and generally they mainly focus on how the information is being presented. So side channel attack is also a very important concept, and that has to be studied, and different mechanisms are there in the literature also. We find a lot more solutions to overcome these side channel attacks. So what we have seen, if we want to summarize, then what we have seen in, if we have different devices that are connected in an IoT application, they may suffer from majorly these security breaches. The first one is the insecure web interface. That web, whenever they are connected with an internet, that particular interface has to be secured. Generally, the communication, they may suffer from the insufficient authentication. That may be a heavyweight authentication, or it may be like the authentication is not being able to secure the, or it is means whatever the mechanism we are using, it has to be lightweight also. It should be like, it should be complex also. So that trade-off has to be maintained when we are designing any authentication mechanism. Next will be the insecure network services. Then we have seen lack of transport encryptions are there. Then we have different privacy concerns of the different users that are connected together in an IoT, on an IoT platform. Then we have also seen that still the insecure cloud interface is still a major research challenge. A large number of solutions are provided by the different researchers. Then we have insecure software and poor physical security is always there when we are talking of an IoT based smart cities. So this is the layer based attack categorization, that we have different layers, and each layers will have its own complexity, and it will have own set of attacks. So if you are talking of an application layer, then we have seen the data aggregation distortion, or we can say the message modification is a major challenge. We have different solutions. Still, this is a major challenge, that how the distortion can be minimized. Second is, if you are talking of transport layer, that is that majorly suffers from flooding attack, then we have the desynchronization attacks also. So that has to be minimized. Then in the network layer, it will deal with the replay attack. Then we have cyber attacks, spoofed attack, attacks on the routing algorithms, sinkhole attacks, hello flood attacks. We have a large number of attacks when we are talking of any network layer. In the data link layer, it will deal with collision attack, node replication attack. And in the physical layer, the majorly it will suffer from eavesdropping, jamming. That eavesdropping, if we are talking of that in terms of wireless sensor network, one of the major attack is the node capture attack. And if we use some pre-shared keys, the problem is that through the eavesdropping, attacker might know that which key or which key identifier is there with any node. So eavesdropping is a major challenge if we are talking of wireless sensor network. So here we have seen, if we want to summarize what we have discussed earlier, that various security mechanisms, they have been proposed to address the different security concerns which we have discussed. So despite we have a fast development of computer security mechanism, but here the scale and complexity of the generated wireless data is still a challenge. And how that particular challenge will be overcome, or how we can, whatever the solution we are proposing, how that particular efficient trade-off between the different parameters, if we are talking of scalability, if we are talking of communication overhead, computation overhead, processing, latency, different factors are there. When we are talking of the evaluating any performance of any underlying mechanism. So that scale and complexity still need to be addressed. So here efficient visualization techniques have to be, there is a need that it should be adopted by the researchers to bridge that particular gap. Means we need a large number of solutions also, but they have to be in real time applications. They have to be feasible one. So what we have discussed the smart cities, we have discussed there is that why there is a security concern among the different sectors of a smart city. Then what we have discussed is that what is an IoT, why it is very important, and what are the different we can say the issues that are related with the IoT. Because here what happened is when we are talking of any smart city, the security it becomes very important. Why? Because we have a large amount of data, and that is generated by the interconnected devices, and these devices they are running different applications. Here the nature of the information is also very dynamic, and here the large number of devices and objects they are connected, and these devices have different functionalities, capabilities, characteristics, and obviously have different internet protocols. So majorly what happened is that there are different issues or challenges when we are talking of an IoT based smart cities, and we have different kind of attacks also. So before coming to the key management, let's start with, or let's we will be classifying the different IoT attacks also. So majorly the IoT attacks they can be classified as passive and active. In the passive attacks, the attacker it will listen and it will analyze the traffic that is generated between the different objects, and without making any modifications. So here the example it may be an eavesdropping where the attacker it will determine the useful information. It can be the keys, it can be the secrets, or it can be the keying information that can be used to launch any active attacks. If we are talking of active attacks, here the attacker it will modify or it will remove the exchanged data, or it can inject new data. We have seen different attacks at the different layers where we have seen a large number of attacks in the transport layer and all. So these are kind of an active attacks. For example, man in middle attack is a very means important attack, and we find a large number of solutions for that also. So what we have seen that if we are talking of an IoT in wireless sensor network, we have found a large number of challenges. So the first challenge is that it is inherently distributed. So here the IoT applications, what we have seen, they are distributed in nature. Means they will deal with the video of different kinds. Then we have the different type of systems design. So how we can develop a common approach for development and designing of the different mechanism is a very important challenge. See here. So here the first, if we are talking of any challenge, the first challenge is simply that the different applications they are inherently distributed. Next, we have seen that how we can manage the data. A large number of heterogeneous devices are there, which we have different that are working on different protocols. So a large number of sensors, they are connected, they generate a large volume of data. And even these devices, they have different kind of attacks also. So we cannot have a single, we cannot design a single security mechanism for all. So there is a need that different different applications, they have to have a different security mechanisms. But how we can provide a interoperability between the different security mechanisms is itself a major challenge. So several problems what we have seen in IoT applications, they arise because there is an interdependence among the different applications. And there is a sharing of the resources also among the different applications. So here the services, whatever the services, they have to take care of the different application that they will not conflict with each other. So here the major thing is that how we can detect and resolve such issues. So what we have seen that whenever we are designing any security mechanism, it has to be efficient one. Efficient in the real time applications. So security is itself an overhead. And if we are talking of IoT application in smart city, different sectors, they are connected. So heterogeneity is also there. There is a high computational and processing requirement at the edge level devices also. So one thing is that it should be efficient. Second thing is the security has to be maintained because a large amount of data is generated. The IoT application, they suffer from large number of attacks also. Different kind of attacks are there. So how to maintain a trade-off between these two is also a very important research domain. That whatever we are designing, it has to be efficient also, it has to be secure also. But these two things are very opposite to each other. If you are talking of security, if we are talking of a heavyweight security, it will incur a large overhead on the terminal devices. So here the question is that how we can make a trade-off between these two. So yeah, whenever we are designing any mechanism, we have to see that it should have the least, it should have a good scalability. It should have an effective data storage also. Processing of data, it should be done at the terminals, but the processing will be least. So we can do the processing at the entities which can handle a large amount of data. Right. So here, then what we have seen that it is an monitoring aware or interactive or efficient applications are there that are interacting with each other. So whatever we are designing, it should have it should incorporate the latency concern also. And because they are the applications, the different sectors, they are interconnecting with each other, they are interactive, they are generating a large volume of data. Even whatever the data they are generating, we cannot that data is in a bursty mode. So different applications are there, different applications, they are generating different data. So we have what we have seen, we have a large number of research issues or challenges that are there due to the interconnection of the different sectors if we are talking in terms of smart cities. So now we are coming to our major main issue, that is the key management. So key management is, if we want to define any key management is a set of processes which will deal with how we can generate the keys, how we can distribute the keys, and how we can maintain the keys after the keys are distributed to the different end devices, how the keys are maintained. If the node is compromised, how the key is revoked, and how the next new key generation is done. So before designing any key management for an WSN based IoT application, we will be discussing with the different requirements of that key. So the first requirement for designing any key management is security. Whatever the key management we are developing or designing, it should be able to support forward secrecy, backward secrecy, and key independence. Forward secrecy means that we will be preventing a node that have left the group. If you are talking of any group communication, what we have seen that large number of users, they are joining the group, then they are leaving the group, again they are joining the group. To make that particular communication a secure one, so the member that have left the group, it should not be able to hear the data. So whenever a member that is leaving the group key has to be changed so that we can maintain the forward secrecy, so that the member that have left the group, it will be prevented from reading the future exchanged messages. So that is itself a major challenge, that how we can maintain the forward secrecy. Because if you are talking of any group communication where the users are very dynamic, see if we are talking of a VANET application, if we are talking of any satellite application also, where we have different IoT devices and they are very dynamic. So how we can handle that dynamicity? Because user is just joining the group, it is leaving the group. So here what happened is, if we have a large number of users that are very dynamic in nature, they are joining the group, then they are leaving the group again, then the key management designed for such group communication, it will generally suffer from a large number of communication overhead. Because whenever a user leave the group, other members have to be given a new. So obviously, if the other members will be given a new group key, and if we have a large number of group, then communication overhead will increase. So that is a major factor, that how we can deal with that forward secrecy. So one of the solution which I have seen in the literature is that we can go for a batch rekeying. Batch rekeying simply is that instead of whenever a user join a group, whenever a user left that group, so whenever a user leave the group, we will not change the key. We will wait for some time, and then we will be collecting a batch of the different join or leave of the particular of the different users, and after that we will be changing the group key. But if we have diluted the forward secrecy, the security is diluted. So how we can make a lightweight key management that can support the forward secrecy is a major research challenge. Still, it is a challenge. And we are working on that particular issue also, that how we can maintain the forward secrecy with least overhead. Next will be the backward secrecy. If we are talking of a group communication, then how we can prevent an object that has just joined the group from reading the yet exchanged messages? Means at the time when the user has joined the group, before that it should not be able to read the previous messages. That has to be maintained. So how it can be maintained? Obviously by generating a new group key. Then key independence also means, if that is a very important concept, that if particular key is disclosed, if the particular key is compromised and the attacker comes to know about that key, it should not affect the other keys. But if you are talking of any symmetric and symmetric key distribution, or if you are talking of a group of users that are sharing the same key, then how the key independence is achieved? Because if the group of users are sharing the same key, and if that particular group key is compromised, then obviously the communication of the among the group is also compromised. Next will be that whatever the key management which we are designing, it has to maintain the quality of service. Quality of service we are talking of in terms of low bandwidth overhead. And if we have a large number of group, obviously it will have a large bandwidth overhead. So here the key management protocol, It should not introduce the exchange of a large number of messages. So whatever we are designing, it should not introduce a large exchange of messages, because if during a key exchange, if large number of messages are generated, then it will lead to a large bandwidth requirement. So that quality of service has to be maintained, that whenever there is a key exchange between the different devices that are agreeing on a same key, before the actual encryption of the data starts, it should, the number of messages, it should be small, it should be less in number. Next is very important factor is one effect SAN. A key management protocol generally suffers from this phenomena that whenever we are changing a group member, it will affect all other members. If we have n members, if one member has left, then other members, n-1 members, they have to change their key. So whenever a user is leaving the group, whenever a user is joining the group, so during the node addition or node deletion, or a user addition or deletion, the problem here is that the one affects n problem is there, that other group members, they are affected. So whenever we are going for changing the key, each time a member it changes, so through the leaving or joining the group, then the other group members are affected. So how that effect, one effect n, can be minimized? So we have seen different solutions for minimizing the one effect n. One such will be the tree-based key management scheme. Another we have seen is the clustering effect. We can have a small cluster of users, and these small cluster of users, they will be maintaining different hierarchies of keys. So instead of having a single key, we can have a different hierarchy of key, and different hierarchies of key, they can be means they can maintain the quality of service by reducing the one effect SAN. Now here the problem is in the one effect SAN is that if the key size is very large, the problem one effect SAN become more, it become worse in fact. And if we have a large number of users, if the user are very dynamic also, obviously it will the effects are very large. Then if we are talking of the key server or the user, it can be, if you are talking of a key distribution which is centralized in nature, then the key server or the end user that is using the key for data encryption, it should have a minimum storage, minimum key storage. So if we are talking of clustering, that we have means the large group is divided into number of small groups. It will increase the number of keys to store, especially because if it increase the number of keys that are to be stored, then it will always lead to more overhead on the users also. Because generally the IoT devices, they have a memory constraints. So if they are memory constrained, lightweight solutions has to be developed. So here minimum key storage is very important requirement, that we have to minimize the number of keys that are used to store either in the key server or either in the user, so that the different memory constraints can be met effectively. Next is low computation overhead. That is also a requirement, that a key management protocol, it must introduce a low computation, especially for the objects with computational constraints. We have seen even in the smart cities that different devices, they have a large number of computational constraints. They are small lightweight objects that have a limited memory. So that the key management that are designed for these resource constrained devices, they should have a low computational overhead. So all in all, key management is the set of processes that support the key establishment and the maintenance between the valid parties according to a security policy. So that is the definition of any key management, that it is the set of processes that will support the key establishment, and it will how the key is maintained between the different parties, between the different devices according to a security policy. So generally the key management, it will deal with the generation of the key, which entity is generating the key. After that, it will deal with the assignment of the key, how the particular keys are assigned, and how the keys are distributed. So it will deal with generation, assignment, and distribution of the network keys. So here, secure communication in wireless sensor network, it should be done without any overhead, but key management itself an overhead. It should have a low communication, computation, and storage overhead. So that itself is a major challenge, that we want to secure the communication, but without any overhead, with low communication, computation, and storage overhead, because the devices that are dealing with the IoT applications, they are generally very resource constrained. They support all type of communications. It can be a unicast, it can be a broadcast, it can be a multicast. So if we want to summarize, we can say that efficiency and security are the main issues for key management and distribution. Whatever the algorithm we are designing, it should be efficient. It should have least overhead on the devices, on the users, on the key server. It should have low communication also. It should have a low computation. Still, we want that the key should be secure. And how the key should be secure? If we have a large number of messages that are exchanged, if we because if we have a large number of messages that are exchanged, that will lead to possibly a stronger authentication and a stronger key exchange between the different parties also. So that trade-off has to be maintained, that how the efficiency is maintained, still we want to maintain the security also. So that's why we can say that key management is a very important topic, and it is a very means that topic, we have large number of solutions for the key management also, and that has to be seriously dealt with the different researchers, that how we can maintain the efficiency, how we can maintain the security. See, we have different requirements. Security is there in terms of forward secrecy. Security has to be there in terms of backward secrecy. Security is there in terms of key independence. If in terms of quality of service, we want that low bandwidth should be there. So if we are talking of low bandwidth, then we have to dilute forward secrecy, or we have to dilute the backward secrecy. If we want that one effect send should be minimized, then we have to dilute the security. But instead of diluting or means making it a lightweight, that lightweight still has to provide the low bandwidth with forward or backward secrecy. It should have a minimum key storage. Now here there is a question. If you are talking of that less number of keys has to be stored, then if less number of keys are stored, it should have a minimum overhead on the users. But it should have, the problem here is that it is not very secure. The key has to be exchanged. The key has to be changed. But if we are talking of that key has to be, because every channel has to be secured, not by a single key. If two devices are communicating, they should have their own set of keys. If a device is communicating with the cluster head, it should have a own set of keys. If the device is communicating with the base station, it should have a own set of keys. So that is how we can make that particular communication channel secure. But here the problem again is that overhead may increase. That has to be minimized. So the problem is that trade-off. The problem is trade-off, how we can maintain that trade-off. These are the different application areas we have already discussed when we are talking of the smart cities, that smart buildings, vehicle tracking, security surveillance, agriculture, healthcare. We have different applications, and every application they require secure communication. For secure communication, we need some secure key management and the distribution of the different devices. So I think we can take a 10 minutes break, madam.
Yes, sure, ma'am.
Okay, we can take the 10 minutes break, and after that we will be rejoining at 8:10. So is it okay with you, madam?
Yes, ma'am. Perfectly fine.
Okay, after that we can join. Thank you.
Yes. All the participants, please be in the meeting. We will be back in 10 minutes. There's a 10-minute break, but don't leave the meeting. The meeting will be on.
So a very warm good evening again. So should we start? Okay, then I will wait.
Yes, ma'am, please.
Okay. In the first session, we have discussed the smart city, the different sectors of the smart city, the applications of the smart city, how the different sectors they exchange the information. Then we have proceeded to the different security challenges in IoT based smart cities. Then we have discussed that as large number of devices and objects, they are connected with one another. And these devices we have seen they have different functionalities, then different capabilities, and how the interoperability between the different devices will be dealt with. So that is a major challenge. So we have discussed different kind of challenges that are associated when different devices with different functionalities they are interacting over an internet. After that, we have discussed that why we need the security, because here a large amount of data from the interconnection among the different application is generated. That data has to be maintained, that has to be secured. Now the problem here is that where it has to be stored, where the data processing is done, where the security will be done. It can be done either at the terminal devices, that is the edge computing, or it can be handled at the middle layer, maybe a fog computing concept. So all in all, we are talking that whenever we are talking of any security algorithm or mechanism, it has to be scalable also, it has to be efficient also, it should be heterogeneous also, it should support the heterogeneity among the different devices. Then effective data storage is also required if we are talking of any smart cities. High computational and processing requirement at the edge level is there. After that, we have proceeded to the key management, the definition of the key management. Then we were discussing with the functional requirements of the key management. Then what we have observed that the efficiency and the security has to be maintained when we are talking in terms of the key management. Now, we will be talking with the classification of the key management. We have talked about the key management, the requirement of the key management. Then we are talking of the classes, how we can classify the different key management. So here, the key management, majorly we will be classifying the keys into three parts, into three classes. The first one, it can be the group key. Group key deal with the group communications. The second one is the pairwise key, where a pairwise key will be maintained between the two end devices. Or it can be a cluster key also, where we are talking in terms of a multicast applications, where a group of users are there. Then we are talking of a network key also. So we have different kind of keys, and each key will have its own different functionalities. So in terms of the wireless sensor network based IoT applications, the key management schemes, it is generally classified into three types. One will be based on the network model. So network model, it can be a centralized also, it can be distributed also, that different users, they will be connecting and they will be generating a key. Centralized key management, they generally suffer from a single KDC, that if that particular key distribution center, it fails, the complete key distribution crashes. So the problem is that the bottleneck here is the centralized key distribution center. Now, if you want to make it distributed, it has other factors also. If we are talking of an hierarchical model, that suppose we have different entities and each entity will be generating a key for different group of users, then that will also be a very means it will generally lead to large number of keys at the terminal end. At the edge device, if we are talking of any hierarchical model, it will lead to large number of keys that are maintained by the devices. So each model will have its own inherent challenges. If you are talking of the probability of the key sharing, that if suppose we are talking of a probabilistic key management, where we have a pool of keys and from there randomly the keys are given to each of the devices that are joined there in a network. So that key, maybe the two devices they are able to share the key, or maybe the two devices they are not able to share the key. So if we are talking of the based on the probability of the sharing of the keys, it can be probabilistic. One such classification is probabilistic, where different users they are sharing the key, but with the probability. So it can be that different users they are not sharing any key because from the pool the key distribution server has taken the key, and the user they are not able to find any common key, because the key distribution here it is random, it is probability based. So if the key distribution is random, some of the users, some of the devices they are not able to have a same common key. So that is an issue with the probabilistic key management. Next comes the deterministic key management. In the deterministic key management, what we have seen that they will always be able to share any key. So in the deterministic key management, we have a class that is a polynomial based key management. Then we have another class that is a matrix based key management. We have large number of other classes also. Majorly, we have worked on these classes. That's why I'm talking of these classes. So these polynomial or matrices based scheme, they are deterministic in nature, where the different users, they are sharing the keys, but they will always share a key. There is no such case where the different users, they may not find any same key. Then there can be a hybrid mode also, where we have different, suppose we have combined the polynomial and a matrix based scheme to generate any symmetry key between the two end devices. So based on the probability of the key sharing, the key management schemes can be classified into probabilistic, deterministic, and hybrid. If we are talking of any communication model, it can be a unicast between the two devices only. So if it is a unicast, obviously it will have a large overhead. It can be multicast because sometimes different applications they require different kind of information sharing. So if we are talking of multicast applications, group key management is a very important concept. Then it can be a broadcast also. So based on the communication model, different key management can be designed for unicast applications, for multicast, and for broadcast. And each will have its own inherent challenges. Now we are talking of the group key management schemes. In the group key management schemes, it can be like network dependent, it can be network independent also. So these are the different pool of the keys which we have studied, or we can say that potential researchers, they can study if they want to work in group key management. Then majorly the group key management, it will be classified into three types. One is centralized, other is decentralized, and other will be the distributed schemes. So here we have in the centralized schemes, we have a one key distribution server, and that will be generating the group key for all the users. So how that particular group key is generated, it will depend on the different mechanism that how that key is generated. So the model by which we are generating the key, it will itself be deciding that what will be the overhead associated with that particular group key. So we can have a one-way function chain trees. We can have a one-way function trees. We have already discussed also. Then we have a efficient large group key protocols. LKH. Yes, anybody wants to ask something? Okay, logical key hierarchical protocol is also there, which is a tree-based protocol that is used to distribute the keys. Then we have a centralized flat table. So these are the different mechanisms by which we are generating the group key, and each mechanism will have its own problem. So if we want to classify, if we want to summarize the challenge, one such challenge will be the joining. At the time of joining, it should have least time. Whenever a user want to join, it should join that particular group with a minimum time. Next will be the leaving. If a user wants to leave the group, it should leave the group within minimum time. And whatever the new group key that is distributed among the user, it should have the least time. Processing time should be minimum, overhead should be minimum. Then secure, lock, and hack. These are the different categories that belong to one such classification, centralized schemes. Then we have decentralized also. In the decentralized, we have large number of schemes where large number of users, they are distributed in nature, and each user they will be communicating with one another to generate any key. Now here we have seen different solutions in decentralized schemes. Once a solution, they are using the trust-based management schemes to just dilute the forward and backward secrecy also. Then we have distributed schemes also. So these are the example of the distributed schemes. So all in all, we have three types of classification of the group key management schemes. Now, when we are talking of any key management, what will be the open issues that has to be addressed when we are proposing a better key management system? The foremost one is lightweight. It should be lightweight, because what we have seen that security is an overhead on the system. So that has to be lightweight. That there should be minimum processing at the terminal nodes. There should be minimum communication overhead, and the latency, it should also be minimum.
ये बिछा रखी थी
इधर आपका विषय ही तेरा ही
हाँ तो ये वाली मैंने वहां वाली निकाल दी।
Okay, next one is the heterogeneous nature of the communication devices. If we are talking of key management, what we have seen that the devices have different capabilities, have different functionalities, and because of that, the different communication devices, because they are heterogeneous, they are using some different internet protocols also. How that heterogeneity Am I audible?
Yes, ma'am.
Okay. Okay, then I will resume. Okay, so here, so heterogeneity of the different communication devices has to be dealt with. The different devices have different capabilities. So how that heterogeneous device, they will interact with each other, and how the single key management solution can be used to address that heterogeneity has to be well addressed. Then is the scalability. So whatever the device they want to enter into a group, The key management, the proposed key management solution should be able to support the devices. Maybe a large number of devices can enter into a group at a time, or maybe the group will squeeze. So it should address the dynamic behavior of the users also. Then it should have an proper adoption of the topology of that network topology also. And third, next one is it should be flexible also. It should be adaptable. Even if there is some change in the network protocols, if there is some change in the architecture, the key management system, it should be able to deal with that also. It should be able to self-organize. It should have it should also have a resilience property. That is very important one. Resilience property. Resilience is simply that if we are talking that sometimes some of the keys, wait, अरे क्या शोर हो रहा है यहाँ पे? Okay, I will restart. Sorry for the interruption. So it should be the solution, it should be scalable. It should be extendable also. There is a concept of key refreshing. Because if we are able to refresh the key again and again, obviously the protocol, the underlying protocol is more secure. But key refreshing with itself adds some overhead on the system. So that has to be dealt with. That if we want to refresh the key, if we want to go for any key renewal, that has to be deal with, and that should have a least overhead on the other users also. The key management should also support the key revocation. Revocation means that if the device that is sharing the key is compromised, the key has to be changed, the key has to be revoked, and the other users, they should not use that key. So there should be some renewal policy. That's why we are talking of the maintenance. We are not talking of distribution of the key. There is a concept, there is a concept of key management system. Key management means generation, distribution, and then the maintenance. Maintenance of the key in terms of key refreshing, key revocation, and the renewal policy. It should be faster. It should require less storage, computation, and communication. Then, if there is some group communication, what is the role of the key management and distribution? The first one is that how we can maintain the confidentiality in the groups. If we don't have the group key, how we can maintain the confidentiality? That's why there is a requirement of the key management. How we can maintain the integrity of the data? What we are talking of scalability, access control, how we can authenticate the valid users, how we can make the service available, how we can make it versatile and efficient. So for all the properties that we want to maintain in a group communication, there is a requirement of key management and distribution. Otherwise, we cannot sustain these properties in a group communication. Come to the major problems and their consequent challenge of the group key management. The first and the foremost is the scalability overhead. Sometimes a group might increase the number of members that want to go into that particular group. They may increase. Sometimes the group may decrease. So there is, if the user are very dynamic in nature, the scalability has to be considered. If we have a large number of users, there is a problem of one-to-one effect that has to be reduced. And if the number of users are less, then obviously it has to be lightweight also. So scalability overhead is a very important concept. So that has to be dealt with when we are designing any group key management for any secure group communication. Storage overhead in terms of the supporting, we can talk of the keys, that it should have less number of keys that are to be stored by the end terminals. We also want there should not be any single point failure. So if we are talking of any centralized group communication, they generally suffer from a single point failure. So how we can ensure that there should not be any single point failure? Next is whenever a user leave the group, how we can maintain the forward secrecy? If a user join the group, how we can maintain the backward secrecy? Then there is a collision independence also. Collision independence is simply that different users, suppose if you are talking of any key, that should not be same. There is always some different key that is generated. If the key that is generated may be generated again after some time, there might be a chance of the information leakage that has to be stopped. That should not be there. So we are talking that whatever the key generation mechanism we want to generate, it should be collision independence. No two same keys will be generated. So here I have summarized the different research issues in the key management and distribution for the future researchers. So here what we have summarized according to the different entities that may involve in a secure communication. So if you are talking of a key server that is generating the key, it should have a low storage. Whatever the distribution mechanism we are using, it should have a low storage. And whatever the key we are generating, it should involve low computation. So here generation and distribution should have low storage and computation. Similarly, same thing again will be for the group server also. Then if we are talking of quality of service, then the key management should be designed in such a way that availability of service should always be there. Is my voice audible?
Yes, ma'am.
Okay. So here the quality of service has to be maintained. Means availability of service is there. Then it should have low bandwidth. Whatever the key management we are talking, it should have low bandwidth. But If you're talking of low bandwidth, how the security features will be incorporated. If you're talking of one-to-one effect should be low, we want minimum delay. Number of messages that are exchanged during the key distribution should be small. Number of the periodic refreshing of the key should be small. So that will lead to minimum delay. But if the key refreshing time is not very frequent, the security will be diluted. If you're talking of any performance problem, then key storage efficiency, communication efficiency is there. So here, if you're talking of any security performance evaluation of any key management distribution, it should be key independence. Always a new key will be generated. It should support backward secrecy, forward secrecy, collision attack freedom, then group safety during the member change, and group key and supporting key. We have seen different solutions. Some solutions, they have the backup key also, so that the communication overhead, it can be reduced. Then we have taken some of the relevant keys that are related with that particular group communication. So if we are talking of that, the main thing is that there can be some pairwise key, there can be some public keys. So here, how the key is generated, some of the keys they are tree based, some are hash key chain based, some use distributed spanning tree to generate any group key. So when we are evaluating any group key management scheme, rekeying is one such factor. So efficient, it should be efficient in terms of energy, computation time, storage, and communication cost. So here, the rekeying and refreshing should be there. It should have low cost, low overhead. But the problem is same, that if we are going for low overhead, low cost, less rekeying, less refreshing of the keys, it is not secure. So here, why the group key management is important? Because it gives many services to any secure group communication. That group key management establishes the keying relationship between the various trusted parties that are involved in a group. And it also provides services for the group communication administration also. So it paves a way for the secure communication among the different parties. And it should provide low computation, communication, and storage overhead. Meanwhile, whatever the group key management we want to give, it support multicast applications, unicast applications, and availability. So these are the various steps when we are talking, these are the phases of any group key management we already discussed. Initially, the group key is generated, then the key is distributed, and after that, if there is some compromised, then key is updated, or either the user leave the group, the key is updated, either the user join the group, the key is updated. So different events are there that will provoke that will make the key to update. So these are the different issues or requirements of group key management we've already discussed. These are the challenges we have discussed. Now this is a challenge for the decentralized group key management. The distribution of a key message, how the distribution is done to a subgroup, because we have to maintain a controller for that group. How the controller is elected, how the if suppose there is some problem with the controller, how we can maintain that it is a trustworthy. Trust relationship has to be, means it has to be evaluated when we are talking of any subgroup communication, and how the authentication is done among the different group members. So if we are talking of conclusion of a group key management, we have observed that group key management, it will ensure the safety and secure connection within the group of keys. It will, we have analyzed the different group key management for the security and performance queries. And after that, we have seen that forward and backward secrecy has to be maintained. Rekey time is to be determined on every leave or join operation. So what we have seen that different T structures can play a major role in decreasing the overheads. Now come to the pairwise key management. So we have discussed the group key management. Then we are talking of the pairwise key management. So here, the task of generating the pairwise key, it can be centralized by a key distribution server. It can be decentralized, that the decentralized, they operate on a network that will be partitioned into fixed number of small groups, where each group is controller, and that group controller will distribute the keys among the group. Here it can be distributed also. The responsibility of key distribution center is shared among the group controller that are usually organized in a hierarchical structure. So here the nodes, they will collaborate to ensure the key management operation for like key generation, distribution, renewal, and revocation. So we again, if we are talking of key management, set of process and mechanism that will support the establishment, generation, maintenance of the ongoing key relationship, maintenance in terms of key refreshing, key updation, key revocation. So goal, if you are talking of goal of a pairwise key management, same is as the group key management. It should be able to provide the confidentiality, that it should protect the data from attackers. Key management, it should provide a mechanism to protect the keys so that the data will not be revealed. It should be scalable also. The key management, it should provide the key for the to the network, but also to larger one. It should be flexible also for the different node addition, and even it should be able to work in hostile environment also. The concept is in the probabilistic key management we are talking, there is a concept of resilience. It should be resilience against the node capture. As we have seen, the sensor networks, they are usually deployed in hostile environments. So they majorly suffer from node capture. So if the adversary capture any node, key management, it should prevent the revelation of the keys to the other nodes in the network. The network resilience should is there, means it should be resistant. If any key is captured, that key should not be used as a link key by the other nodes. Revocation, if any node or device is captured, then it should remove the node dynamically from the network. So it will be the group controller, key distribution center. It can be a distributed model. It can be a centralized model. It can be any model. So that should support the node revocation. So what are the different security objectives? Availability, integrity, confidentiality, authentication, and non-reputation. These are the different security objectives when we are talking of KMS. Now here, if you are talking of the phases of a key management scheme in pairwise key distribution, it will relate with generation of the key. Now here, different models, suppose if it is a centralized one, the key distribution server will generate the key. Then how the key will be distributed? It should be distributed with the minimum overhead. Then there is a revocation. If suppose some device is compromised, then how that particular key will be revoked? Then how the new key will be assigned? So generation, distribution, revocation, and new key assignment. So these are the four phases, major four phases of any key management. Then comes a classification of key management schemes. In terms of, here we are talking of pairwise key management. In earlier we are talking of group key management. Now we are talking of the pairwise key management. So here we have two kind of keys. One is the symmetric, one is the asymmetric. In the symmetric key management scheme, we have single shared key schemes where the complete network it is sharing the same key. But that were the earliest network because they have no security now. Because if suppose one node is compromised, the complete key is compromised, set of keys compromised. Then comes a pairwise key distribution where different two devices, if they want to connect with each other, they have their own pairwise key. Then we have trusted third-party based schemes where if two devices are not able to generate a key or suppose they want to communicate with one another, then they may trust with some other device and that device will generate the key for them. Then we are talking of probabilistic key distribution where we have a pool of keys and with the probability the keys are given to the different devices. So maybe they have the key, maybe they share one key, maybe they share two keys, or maybe they share all the keys, or maybe they share none. Then we have matrix based schemes and polynomial based schemes. These schemes, they are deterministic in nature. They always share some key. So they have the connectivity. 100% connectivity is there in matrix based and polynomial based key distribution. In the asymmetric key distribution, we have RSA based key management and ECC based key management. Now we are talking of the key revocation and rekeying and all. So what is that key revocation? So whenever a device is compromised, its key have to be revoked. If we are talking of a probabilistic key management, where from a pool of keys, different keys are assigned to different devices. So there might be a probability that the key that is given in one device, it may be shared by other device. So that key has to be revoked by the base station in the network by means of rekeying. So if there is large number of compromised devices in the network, it results in large number of revocation messages in the network. So what we have seen in the basic rekeying scheme, that if the current key means, because it is a probabilistic based mechanism, so different different devices, they may share same key. So different set of device, they may share the same link key. So if suppose that key is used by the communicating device and that is compromised, so what happened is that the device that are sharing the same key, they will start searching some other key so that they can communicate. Now that may lead to a problem. So we have given a solution for that problem. We have proposed one scheme for that. So in the basic scheme, what we have seen that it is used to discover the other link key. Sometimes we go the user the nodes they go for path key establishment also. So during the dekeying process, it results in more communication and computation overhead. And it also suffers from major connectivity problems. Sometimes the two nodes, they don't find any common key with them. Or maybe the key that they use will be compromised due to the capturing of some device. So now what they will do? They will go for path key establishment. So this is a problem that during that process of key establishment, the normal data communication is also interrupted because the key that is used to encrypt the particular communication is compromised because the device that is containing that key is compromised due to the probabilistic key distribution. So sometimes some of the keys are heavily, because what happened is in the probabilistic key distribution, some keys are heavily used by more links, some keys are not heavily used. So the keys that are heavily used by some nodes, if they are compromised, they will compromise the complete network. So it will lead to, sometimes it will lead to total disruption of all those links. Now, key management schemes in wireless sensor network based IoT platform. So for that, majorly they are classified into the earliest most scheme was EG scheme. It was a probabilistic key management scheme where we have end-to-end encryption, CPU energy efficient was there. It was very simple to implement and it have an excellent scalability. But limitations were that if the number of capture nodes increases, the performance will decrease because it will lead to more node revocation and rekeying. Large memory overhead was there in the EG scheme. After that, in the EG scheme, that there was a property that two devices they can communicate with one another if they have one key, common key. But now we want to increase the strength of that particular link. So we, instead of having one key, there was a Chan et al. It has introduced another scheme that is a Q composite scheme. So these schemes, they are very largely cited schemes. If we are talking of key management, we always, if we are talking of key management, particular if we are talking of probabilistic key management, so these are the basic schemes that are used by the different users. So in Q composite scheme, it has a dual key pools. And in the Q composite scheme, instead of having one key shared, it will share the Q key. So it, in a way, it has increased the key overlap between the two devices. So if it has increased the key overlap, it has increased the strength of that particular link key. So if we are comparing it with EG scheme, it increases the resilience against the node capture with Q common keys. But again, it has a limitation, lower key connectivity and susceptible to large scale attacks. Next, there is another enhancement, another scheme that is a deterministic scheme, that is a polynomial based scheme. So it is a secure and T collision resistant. Up to T number of nodes, it is secure. So after T nodes are captured, the complete set of keys are revealed to a attacker. Because we are storing the polynomials, it will have generally large memory overhead and computational overhead. Q composite and EG scheme are random scheme. These are polynomial scheme. Next comes, there is a very beautiful, we can say, distribution that is called the asymmetric. In the previous three schemes, what we have seen that the key ring or the number of keys that are assigned to any device is same. But in asymmetric key distribution, what we have seen that the keys are not same. So in the asymmetric pre-distribution, some nodes are given large number of keys, some nodes are given less number of keys. They are applicable in the heterogeneous structures. So they are very energy efficient. In terms, if the node capability is more, we can store large number of keys. If the node capability is less, we will store less number of keys. So processing overhead on these resource constrained device is less. But a connectivity will be same because the pool is same. But we have make it asymmetric rather than symmetric. Then another class of scheme is there where we have deployment based scheme. In the deployment based scheme, it uses the we can say it uses the structure, actual area on which we are storing the sensors, on which we are deploying the sensors. Based on that deployment information, we will be storing the keys. In the EG scheme, what we have observed that the keys, sometimes they may not share the same keys. But in the deployment based schemes, what we have seen that based on the information that if we know that these devices are the neighboring devices, then we can share more number of keys with them, so that there will always be a key and they can start the session in a hassle-free manner. So here deployment information is being utilized in order to distribute the keys. Now the rekeying solution. If you are talking of rekeying solution, we have two schemes. One is the EG scheme. It is 1 to n. So here the compromised key need to be revoked from the non-compromised nodes. So what was the weakness here? That large communication overhead is there. And whenever any key is compromised, then shared key discovery will start. In the probabilistic key management, we have different phases of key. One will be the key generation, then it will be the shared key discovery. In the shared key discovery, different users, they will share the key identifiers, and based on the key identifiers, the different nodes, they will assess, okay, they are sharing the same key or not. During that shared key discovery, the normal data communication is interrupted. Next comes the Biswas scheme. That is a fast rekeying scheme. And here what happened is that frequently used key is given higher rank and it is ignored during the shared key discovery. And because it is a probabilistic key distribution, so we know that this key, because KDC will know, okay, this key will be stored in many number of nodes. So obviously there are more chances that this key will be used as a link key. Right? So there are more chances of it. So here the lower rank key is used as a backup key. Because now we have two keys. When one key is revoked, and that is the existing link key, the device, they will opt for the second key. So there is no need for going for the shared key discovery. That will be omitted. So if that phase is omitted, it will lead to less number of rekeying messages, and then obviously the resulting communication overhead for that rekeying model is reduced. But here the problem is that only we have seen that frequently used key and less frequently used key. And based on it, we are giving the rank. Next comes to another class where we have studied and analyze the behavior of an adversary, that how it will behave in a network. And based on the behavior of the network, we will be defining the key management solutions. Now here, we have assumed that the network is graph based. So one such scheme will be hash based scheme. In the hash based scheme, we are using the hash chains, or we are using the hashing, and we have exploited the one-way property of the hash, that if we have used the hash, then backward key cannot be determined. So based on that, if suppose any attacker has obtained the key that is at the last of the chain, it is not, it does not come to the back. So it cannot get the original key. So here the nodes, if they got the key that is at the last of the chain, and if they get compromised, they will not be affecting the keys of the other nodes. And if the node that is on the first means that is containing the original key or one hash key, then obviously it will lead to more we can say the less network resilience. So resistance of any network using that particular hash chaining will depend on where that particular means at which place the key is compromised. If it is at the end of the chain, obviously it will affect less number of nodes, and if it is at the middle, then now average number of nodes are affected. Then we have two level key pools. So here, instead of having one pool, we have different level of key pools, and it is also using the deployment based key. Then different levels, they will be communicating with different key. So if one key is compromised, then it will affect the key of that particular level rather than the other level. So if we are maintaining different levels of the key, obviously it will enhance the security of that particular underlying scheme. Hybrid distribution is simply that we are combining, suppose if we are combining polynomial, then hash chaining, and then matrix based scheme. So we can combine different keys. So if you are talking of key management schemes, one such class will be how we can define or how we can design the keys based on attack probabilities. Attack probabilities means if we know the behavior of adversary and we know that these are the devices or nodes that may be attacked by the adversary, so we can secure these nodes more rather than the other nodes. So the question here is how to model the attacking behavior of an adversary, how the probability of attack can be estimated with different parameters, and can we use the deployment knowledge also? Yes, we can use the deployment knowledge to improve that particular attack model. Next is, there was a question that if we are talking of probabilistic key management, how we can develop the mechanism that may increase the resilience also and that may increase the connectivity also. If you store less number of keys, the security will increase, because if they're compromised, it will affect less number of nodes, but it will decrease the connectivity of the underlying network. How we can reduce the communication overhead and computation overhead of KMS without sacrificing its security and key connectivity. So proper trade-off is there, that we want to secure also, we want to maintain the key connectivity also. In terms of key revocation and dynamic update, how we can efficiently revoke or update a compromised key from a network. We have seen once a solution will be by providing a backup key. Then what we have seen, still there is a problem that none of the existing protocols, they have decided and analyzed the key update period. If the key update period is very large, the problem is that the key will be compromised. There is a probability that the key may be compromised. If the key update period is very small, a large number of leaking is done, messages are generated over a network, and it may lead to poor performance of the network. So this is a scheme. Okay, madam, how much time is left?
Ma'am, the time is over.
Okay, it is over, so I will be concluding it, right? Okay.
Yes, ma'am, you can conclude now.
Okay, so this is the one scheme, one such solution which are given by us. So here we have using the adversary behavior, we have given the rank to different keys, and based on, you can take that paper from me. If anybody is interested, I can share that paper, and I can share that scheme also, where we have ranked the keys according to the attack probabilities. So these are the traveling cost, and these are the capturing cost of any node, how we have evaluated and all. Then this is the rekeying scheme, and how we have reduced the number of rekeying messages in a model. Then these are the different actions, means how we have reduced the number of messages here. Then this is another solution, key management solution. So it will be using the attacking behavior of the attacker. So we have a large number of models that will be using the vulnerability evaluation, and based on it, it will be assessing the risk of any node. So suppose this is an example. So here, this is a grid-like structure, different nodes are there. So based on the neighboring nodes, we can, if we are able to give any attack probability to each node, so we can say that, okay, how many keys will be shared. According to the risk probability, we can share the keys among the different nodes. That can be done by the key distribution server. So these are the different node capture strategies or adversary behavior. One may be the dominating set, because they are these are the nodes that will be carrying major part of the traffic. So if we are able, so we assume that the adversary is intelligent, so it try to means compromise these nodes that are carrying large number of traffic. Then we have matrix based attack. Then we have, okay, if the two nodes are not able to share the key, they can go for the path key. For that, we have a large number of class, that is the proxy, friend based, and disjoint pathways. These are the issues we have already discussed. This is the path key establishment. That is also a major important concept, that if the two users are not able to find any common key, how they can find a common key? By trusted third party. That is the path key establishment. These are the different means we can, the two nodes, they can find, suppose a source and destination, they want to send some data and they don't have some common key. They can go for proxy. They can find the proxy node and then they can share the key. Maybe they can find a friend node also. This is another scheme. Then we have the hybrid key management schemes, where different schemes, they are combined together with one another. This is the hash-based schemes where we will be using some hashing mechanisms. So see here, I will be not taking much of the time. So see here, this is only an example from which we can say, suppose these are the different nodes of a network. And suppose a node is having K1, K2, K3 key. These are the different keys that are means key identifiers that they are sharing. Now what we can do is that if we perform an hash function on it, so if K6 key of F node is compromised, even if it is considered by, even if it is there with D, still the D will not be affected because it is having H2, means 2 time hash is there on K6. So obviously, if F is compromised, it will not affect the D. So in this way, we can say that hashing can reduce the number of nodes that are affected during a node compromise. So this is all. Hopefully the participants, they may gain something. And even if there is some queries, you are most welcome. I can share my papers also with them. I can share whatever the research material I have, and those who want to work in the key management for IoT, for smart grid. I'm working in key management for the smart grid infrastructure also. I'm working in key management for IoT applications. I'm also working for key management in satellite communications. So anybody who is interested is most welcome. I will be sharing my uh, email ID with you. So anybody can contact. I will, and whatever the information the person needs, I will be happily to share it with you all. So thanks again for inviting me for that lecture, and I have winded up my presentation.
Thank you,
So
ma'am.
any
You have
queries are
covered almost everything about key management. So now the house is open for discussion. Any participant? Any question from any participant? Any of the participant is having any query, he or she may ask it to ma'am. I guess there are
I
no questions.
okay. I have shared my email ID also. So anybody who want to means have any query even in the future, they can contact me. No issues.
Thank you very much. Thank you very much, Dr. Alawat, for such a suitable and informative talk. Please accept my appreciation to you for accepting our invitation to deliver this expert talk in this FDP. I truly regard you and your time you spend for us to be on this FDP in online mode. Ma'am, the way you have explained various concerns of security in IoT while implementing smart cities, collection of data, processing of the data from very basics, and protocols to be considered while designing security mechanisms like different key management schemes in very beneficial, it will be very beneficial to all the participants. You have provided countless new ideas to upcoming researchers. Thank you very much, Dr. Alawat, for this brilliant talk. The session was very enlightening.
Thank you again, ma'am, for inviting me for that FTP. And I again welcome or I again if any query from any of the participant is there, they can contact me, and they are all welcome. Thank you.
Thank you, ma'am. Thank you so much. So, dear participants, this was the last day for the online sessions. Tomorrow we will be having off. So on Sunday, it will be off. And from Monday, the offline week will start. So we are having inauguration session on Monday at 9:30 at the basement seminar hall of the auditorium in the university. So kindly be there on time, as the former chief town planner of Haryana, Shri Jaswant Singh, will be our chief guest, and the vice chancellor of the university, chairman of the department, all will be there. on the dais. So please be there at time, because before the inaugural session, we will be having the registration session. So for registration, you have to be there by 9 or 9:15. So hoping to see you all in the offline session on Monday. Thank you so much. Good night, everyone.